Okay, so now having studied a bit about the channel effects and looking particularly at ISI in detail, we will be now looking at the ways that we can handle ISI, and so let us proceed further. So the week's topics that were discussed already, we have done those marked in green. So we've had a discussion on them, and now in this part of the lecture we are going to look at the ones highlighted here in red, so equalization and eye diagram. So before we proceed further, the learning outcomes for this part of the lecture are to study equalization as a solution to deal with ISI, to be able to analyze the eye diagram for qualitative analysis of ISI, and to discriminate between increasing or decreasing ISI. So these are the learning outcomes for this part of the lecture. First of all, we come to the two types of error performance degradation in digital communication. So here we are looking at two different scenarios. In figure A, we have a scenario where it is due to a decrease in received signal power or increase in noise power or interference power, and effectively this leads to a loss in signal to noise ratio or digital SNR EB by N naught. So that is what is being shown here. And the second figure is due to signal distortion, which might be caused by intersymbol interference. So let us say that we require a communication system with a bit error probability PB versus digital SNR EB by N naught characteristic corresponding to the solid line. So the solid line is what we expect from our communication system, that is like our target curve. And let us suppose that after the system is configured and measurements are taken, we find that the performance does not follow this curve, which is expected or target, but in fact it follows the dashed curve, the dashed line. Okay, so considering and discussing this one first, as you can see, there is a loss in EP by N naught, which might have come because of signal loss or increased level of noise or interference. So let's say for a desired bit error probability of 10 raised to the power minus 5, let's say this is our target. If this was our target, the theoretical required EB by N naught value was 10 dBs. But because our system performance has been degraded, we can see from the dashed curve that for the same bit error probability of 10 raised to the power minus 5, now we need a SNR of 12 dB. So that means if we want to meet our required bit error probability, we'll have to increase our EB by N naught by 2 dBs. So it might be a serious problem, especially if we are in a power limited situation. Where will we get this 2 dB from? But you can see this loss is not so bad as compared with the possible effects caused by distortion as shown here. So here again imagine that we do not meet the desired performance of the solid line curve, but it's not a loss in SNR, it's a degradation brought about by ISI. So even if we increase SNR, even beyond 12, as you can see, increasing the SNR, that has got no effect. We cannot still achieve 10 raised to the power minus 5 probability of bit error. There is no way. So what's the bottom line? That increasing SNR does not solve the problems related to ISI. So they have to be dealt with in a different manner. So what do we do? So the cure to that is a technique called equalization, and that's what we have studied, that whenever we have distortion, we go to equalization. So since the distortion effects of ISI, they are caused by filtering in the transmitter and the channel, equalization can be considered as a process that reverses such filtering effects. So that's the idea. So moving on to equalization. For equalization, we need to consider first of all that a communication channel, the frequency response of a communication channel can be represented by Hc of f, which is actually this. It has two components. One is the amplitude response and one is the phase response of the channel. And we have studied equalization previously in communication systems, and in order to achieve ideal transmission characteristics over a channel without distortion, so we studied that within a signal's bandwidth, the amplitude response must be constant, and the second condition is that theta c of f, it must be a linear function of frequency. So these were the two conditions we studied for distortionless transmission, and we know that when this is not satisfied, we will have amplitude distortion. When this is not satisfied, we will have phase distortion, and actually in channels we have a bit of both. So we have both types of distortion. So these distortions, whether in amplitude or phase, they basically translate into dispersion or smearing. And because of this dispersion or spreading or smearing, any one pulse in the received demodulated sequence is not well defined. So we are not clear about where is it starting, where is it ending, and so because it is a spread, it has a long tail and it has gone on to the symbol interval of the next pulse, maybe the next pulse as well. So we have a problem, and this overlap is obviously called ISI, intersymbol interference, and it arises in most of the systems, and it is one of the major obstacles to reliable high speed data transmission over band limited channels. So generally, equalization is any signal processing or filtering technique that is designed to reduce or eliminate intersymbol interference. So equalization is partitioned into two broad categories. The first category is called maximum likelihood sequence estimation, and the second category is equalization with filters. That's what we are more familiar with. So in this MLSE, what happens is that experiments or arrangements are made to have measurements of the channel's impulse response. So the channel's impulse response is obtained at C of t, and then using that channel impulse response, the receiver is adjusted to the transmission environment. So for example, if the channel conditions change, its impulse response will change, and as its impulse response changes, we will make further adjustments in the receiver to compensate accordingly. Now here we enable the detector to make good decisions from the demodulated distorted pulse sequence. We are not actually working on reducing distortion of the pulse sequence. The focus here is how to enable the detector to make good decisions based on the distorted pulse sequence. So the focus is not on removing distortion from the pulse sequence. An advanced technique, just giving you an example, Viterbi equalization. It's not part of the course, but Viterbi equalization is an example of this type of equalization. Now coming over to the second type, the one we are more familiar with and the one which is more popular and followed is equalization with filters. And as the name suggests, it uses filters to compensate the distorted pulses. Now the detector in this case, it works on pulses which are cleaned by equalizer. So the equalizer is doing some sort of processing on the distorted pulses to remove or reduce the distortion, and then it is passing it on to detector for detection purpose. So it is more popular, and once again equalization with filters, it can be further subdivided into two categories. One that is called transversal equalizers, in which there are linear devices and there are feed forward elements, and the second type is called decision feedback equalizer, in which, as you can probably guess, there are nonlinear devices and there are feed forward as well as feed. So going into a bit of discussion on the technique of equalization with filters. First of all, we start with modifying the overall system transfer function equation. We know that previously we represented it as h of f is equal to h of t multiplied by h of c multiplied by h of r. So the overall system transfer function is a product of the transmitter transfer function, the channel transfer function, and the receiver transfer function. So we are modifying that equation. First of all, we are assuming that our overall target is that of a raised cosine filter. So the overall transfer function will equate to the transfer function of a raised cosine filter. And secondly, because we are using an additional piece of hardware called equalizer, so we will include its transfer function in the overall equation. So considering these two, our overall system transfer function equation will look like this, where RC is for raised cosine, T is for transmitter, C is for channel, R is for receiver, and E is for equalizer. So now basically our overall system transfer function becomes a combination of four independent transfer functions, one for each component or each block. Practically, the challenge we face is that we have very little or no idea of the channel transfer function or the channel's impulse response. It's not very well known, it's not very well defined. We might have a few indicators, but we cannot say anything with certainty, and especially with the channels whose behavior is changing and it's not static. It becomes very difficult to use one standard value for the channel transfer function. So we pretty much do not have a very good idea of HC of f. But there is something else that we can do. We can design the transmitter and receiver filters. We can design these components in such a way they will behave like filters, but we enable them to be designed in such a way that their product HT of f into HR of f, that is equal to that of a raised cosine filter. So we can target to achieve this. So what does this effectively mean? It means that HT of f and HR of f, they basically become the square roots of the raised cosine. So this equal to square root of raised cosine, this equal to square root of raised cosine, their product is raised cosine. So hence that is where the name has come from, root raised cosine. So that is what we can endeavor to do in order to equalize. That's the first thing we do, is that we make their product equal to raised cosine. And if you look at this equation, if the product of ST and HR is equal to raised cosine, so basically they cancel each other out and we are left with 1 is equal to HC of f multiplied by HE of f. So basically what happens is that they become reciprocals of each other. The channel and the equalizer, they become reciprocals of each other, and so the equalizer transfer function is 1 over the channel transfer function, and you know the channel transfer function, we know the expression. So if we include that, so this is what it looks like. So this is the equalizer transfer function needed to compensate for channel distortion, which is simply the inverse of the channel transfer function. So that is how we achieve equalization, and that is the sort of the transfer function we will need for the equalizer. And we have studied one or two types of equalizers in communication systems, so idea is the same. In fact, the transversal filter, that's exactly what we studied. So that's about it. That's the end of our discussion on equalization with filters. Now we are going to look at how we can visually analyze the effects of ISI. So the tool that we use to analyze intersymbol interference is the eye diagram or the eye pattern. And basically the idea is to measure the system's response to baseband signal. So whatever system that will introduce ISI, we check its response to baseband signals. Eye pattern or eye diagram is a tool to basically qualitatively analyze the extent of ISI. And there is a certain way in which we make connections to the vertical and horizontal plates of the oscilloscope, but that's the background. You don't need to be familiar with that. It's just remember that this is a display on the oscilloscope with a certain arrangement of connections. And what it does is that once you make those connections, it superimposes the waveform in each signaling interval into a family of traces in a single interval. So basically there is an overlap or an overlay of different signaling intervals on the same screen, and we use a random pulse sequence. So sometimes it will generate one level of the bit sequence, sometimes it will generate another level of the bit sequence, and the idea is to overlay or hold. So the previous trace is left on the screen, and then the next trace is plotted, and multiple traces are plotted on the screen, and the resulting pattern looks like an eye, like this. So these are all multiple traces of the pulse waveform. There is one signaling interval here, and in one signaling interval there is a family of traces. So sometimes here, for example, we have chosen a two level signal with a positive voltage and a negative voltage. So that is some sort of an RZ scheme, maybe an RZL, where a positive voltage represents 1 and a negative voltage represents a 0. And because the pulses are being randomly generated, so sometimes a 1 is generated, sometimes a 0 is generated, so sometimes we have a positive pulse, sometimes we have a negative pulse. So we have a binary antipodal signaling in this example, and the width of the opening indicates the time over which sampling may be performed. So here this is the width of the opening. It indicates the time over which the pulse may be sampled. So if this is increasing or this is increasing in a signaling interval, so basically the central open region is decreasing, so our effective sampling time is decreasing. But there is an optimum sampling time associated, and that optimum sampling time is at when we have the maximum eye opening. So if you can see in this figure, the maximum opening of the eye is probably at this time here, so that becomes the optimum sampling time. If we have an ideal system which has an infinite bandwidth, so it would not distort the pulses, they will not change their shapes, and they will look like perfect rectangle. So for a 1 you have a high pulse, for a 0 you have a low pulse. So basically this eye looks like a rectangle. It has maximum opening horizontally and vertically, with no such distortions if we have an ideal system, but we don't have an ideal system practically. So in this figure, dA, that is a measure of distortion caused by ISI. So the greater is the ISI, we have a greater distortion here, and the greater amount of distortion we have, the lesser is the eye opening here. So, and JT is the range of time differences of zero crossing. So as you can see, there's a whole range of zero crossings here. This is called timing jitter. So the pulses are not rising, they are not falling at the right time. So if this is the signaling interval as indicated by these two dotted lines, the pulse is supposed to start here, quickly rise to its maximum value, or whatever the value of the pulse is at that time, quick rise time, and then the pulse is supposed to end here. So again cross zero here, but as you can see, there is a lot of fluctuation and there is a range of time differences of zero crossings. And this is our noise margin. This is our noise margin from the center of the eye, from the center between these two levels, from their center to this point here. This is our noise margin. So as you can see that the distortion caused by ISI increases, even that decreases our margin. And then ST is sensitivity to timing error, calculated from the center of the signaling interval to the first zero crossing it comes across, that is the sensitivity to timing error. So these are all different parameters used to assess the quality of the channel in terms of ISI. And as we discussed, the cleaner the channel is, the less dispersion a channel shows, the more open will this eye be vertically and horizontally. But if that's not the case, we will have all sorts of problems. So let us look at another example to understand the eye diagram, eye patterns. So the effects of channel filtering and channel noise can be seen by observing the received line code on an oscilloscope. So let us say, for example, it is one of the PCM waveforms, probably NRZL, because it has got a positive voltage for 1 and a negative voltage for 0. And as you can see, it's a practical system, so already the pulses or the waveform is not perfect 90 degrees rectangular pulse, but rather the edges are rounded. So with all near ideal filtering, if there isn't so much distortion and the pulse is not distorted, the eye pattern will look like this, very clean and nice, and with a big eye vertically and horizontally. But if we have a filtering effect with ISI, so our this waveform is distorted further. It looks rather like a sinusoid, and if such pulses are overlaid, overlay, eye diagram is an overlay of those pulses. So for positive pulses, negative pulses, we see all sorts of things. So this is what it will look like, pretty much like the figure on the previous slide. And as you can see, now the eye opening as compared to this figure has reduced vertically and horizontally. And if you look at this even further affected signal, which has noise as well as ISI, and if such a signal is viewed on the eye diagram, we see even worse figure. So as you can see, the noise margin has reduced and we have increased distortion. This obviously remains the best sampling time. So here we are discussing different cases of the distorted polar NRZ waveform and their corresponding eye patterns, and then we are able to obtain certain information from the eye pattern. For example, the eye opening, that gives us an idea of the timing error. The sensitivity can be gauged from the slope of the open eye. Slopes, this slope is higher, this is getting lower, this is even lower. And the noise margin can be gauged from the height of the opening eye, as we discussed here, from the center to this value here. So different types of information can be acquired from the eye diagram, and this is basically a tool to visualize the effects of eyesight qualitatively. It's hard to measure it in terms of volts or units, or maybe you can with the accurate measurements, but it is basically designed to give you a qualitative idea of how eyesight will affect your system. So having an eye diagram very quickly lets you know about the situation of intersymbol interference. So the eye diagram and the constellation diagram or the scatter plot are used together to visualize the communication systems. They are both collectively used. Here I'll show you some figures from a worked example in MATLAB Simulink, which uses both of these features. And you have to remember that in red is the signal that is passed through a noisy channel and then through a matched filter at the receiver, whereas the blue is a noiseless channel which is passed through a matched filter at the receiver. So the red has noise, where the blue one has got no noise. And if you look at the eye diagrams in both scenarios, this is the noiseless signal with a very clear eye opening horizontally and vertically, and this is the noisy signal, the one passed through AWGN. And as you can see what happened to the eye diagram opening. So it very quickly makes you realize that how much is the noise, and this range here can give you an idea of the amount of noise in the system. So you can see that there is a lot of noise, whereas here there is hardly nothing, there is hardly any noise. So both these, the eye diagram clearly shows the variation in the received signal from the transmitted signal due to the AWGN and the receive filter. And now for the same signals, when you look at their scatter plots or constellation diagram, so here we have the scatter plot of the noiseless signal, and here we have the scatter plot of the noisy signal. And once again you can see it scattered away from its mean positions, whereas it is nicely spaced with the sufficient spacing between the symbols. So they clearly show the variation from the transmitted signal in the received signal at the symbol boundaries. So together, as I said, they are used to analyze communication systems. So that brings us to the end of this week's lecture. Thank you very much.